Hello, hello. Welcome back to the AI Catholic Podcast, where we are artificially intelligent and fine-tuned through faith. I'm your host, Vic, and today, hopefully going to be cracking open the black box of LLMs, large language models like ChatGPT, and shining a light into how they actually work, because I know a lot of people, they just go on to chatgpt.com, they put in their question, they talk to it, whatever, and then they get an output. And maybe we don't really think about how this works. Maybe we don't necessarily trust it because we don't understand it. And you might have heard about tokens and embeddings, and you're not entirely sure what those are. So we're going to be trying to talk about that just a little bit. And first off, some pretty big news out of OpenAI. They claim to have finally figured out why ChatGPT and language models in particular hallucinate. If you're not sure what the term hallucinate means, it's when a model doesn't actually know the answer, but it gives false information. This is called a hallucination. It just makes stuff up. There was a paper that came out a couple of years ago, or year ago or so, where a researcher said that we need to call it what it is and that it's bullshitting and these models are just BSing. So there's that. But OpenAI thinks they finally figured out why. And before we go into that, I've always suspected that it was because the models are programmed to give a response no matter what. They want to keep you engaged. That's how these companies are going to keep the business going, keep the user engaged, program the model to give some kind of response. And I've always suspected that we still use a reward-based training system. There's some kind of incentive that is given to the models when they're going through their training and evaluation. And I've always suspected that we put too much of an emphasis on providing an answer and not enough of a punishment on providing a wrong answer. And that's exactly what OpenAI admitted to. They said that part of the problem was the data that they received, that they trained the models on, was sometimes incorrect and inaccurate. And they would have to go in and do fine-tuning and clean the data, scrub it, and to increase its quality. So first off, you need good data to go in to get good data out, good in, good out, bad in, bad out, garbage in, garbage out. And that's a problem we're actually starting to see is with ChatGPT 5. It was also just released. This one's actually newer. Since its release, it's already, I think it's doubled the amount of false information that it has put out from prior releases. So that's not comforting to think about. But anyway, I digress. So OpenAI said that during their evaluation stage of training, they gave 0 points for wrong answers and 1 point for a correct answer. So the model figured out, because these things are actually pretty smart, and it figured out it was better to just guess, because it might be right and it might get a point than it would be to not say anything at all. Because by not saying anything, it wasn't getting a point. So it would just guess. And it reminded me of when I was taking my SATs in high school. We were told you don't get any points wrong, or you don't get any points deducted for wrong answers. So it's better to take a guess. On a 4-question standardized test, that's fine. When we're dealing with something like OpenAI, which is supposed to be a giant codex of all of human knowledge, it's supposed to be knowledgeable and reliable and dependable and able to help us out. You can't be doing that. Um, and so I think that instead, the evaluations should be a little more like how the ACT is graded, where when I took it, um, wrong answers, I think you got like minus half a point or half of a quarter point, and not answering was nothing. You didn't lose points, and every correct answer was a point. And so I think with evals, we should do the same thing, where if the model gets a right answer, it gets a point. If it says nothing, or even if it says I don't know, that's 0. But if it provides a wrong answer, then it gets dinged a point. So it's automatically going to start thinking, I don't want to lose points, so it would be better for me to either refrain unless I actually know the answer, or to acknowledge I don't know the answer. Now, how do we do these evaluations? So we're going to talk a little bit about this, but it's actually really cool. When you take your data set for training, you split it about 80-20 or 90-10, with the bulk of it being for data. And you're going to run it through the model. It's going to get all this data. It's going to map out the tokens and build relationships between words and figure out what word comes next. And then you give it a segment of an input, and it has to then guess what the next half of the input is. And then it's revealed to the model what the full input was, and it'll be graded based on that, the relevance, and how closely it came to predicting the next set of tokens. I've done it. It's pretty cool to watch. So there's that piece of news. We may have finally figured out why language models lie, and part of it, again, quality of data. You get low quality data, you're going to get low quality content. But also we need to rethink the incentive-based and scoring-based training that we do for these models to incentivize them to actually say that I don't know, or to just refrain from answering. The next cool bit that came out was improvements to codecs with GPT-5. And if I understand correctly, there's a SWE, a software engineering benchmark, that codecs is now passing consistently with relatively high scores, like somewhere in the 70s, I think, as compared to other models and other versions of ChatGPT. And part of that is because typically when you ask ChatGPT to help with coding or to do vibe coding, you just put in your prompt and it immediately starts spitting out code. And this has been one of my biggest frustrations, is if it doesn't have the full context, it doesn't ask questions, it just takes you at your word and then produces code. And the code is mediocre at best. You still have to go in and fix it and provide the context. And what Codex apparently does is it actually spends time thinking about the code it's going to write before it actually writes the code. And this is what a lot of software engineers do. We spend the majority of our time isn't actually writing, it's reading. We are reading other sections of the code base that we're going to be working on. We're reading documentation for libraries and features that we're going to be building and implementing. We do a lot of reading to figure out, okay, what's the best way to actually write this out? Because sure, we could write up a form and stick it in a component and shove it onto a website. But if we don't know how the back end, the API is meant to receive that data, the form could be broken. Someone could just put in their data, and as soon as they hit enter, that data might not go anywhere. So we need to actually see, how are these different pieces going to connect? And so now Codex apparently thinks about that. And it can spend up to 7 hours actually planning out how it's going to implement a new feature. And it will ask questions and try to get the big picture and build as much context as possible. Because within AI, context is king. The more context you provide, the better your response. The better the response is going to be from the model. So now we had prompt engineering, but now it's context engineering is kind of the new subfield within AI development that's starting to come out. Now, how does all of this work to begin with? How do these models learn this stuff? And it's really cool. Notes. Okay, so ChatGPT is really unique, and it uses something called a transformer model. There are other chatbots and LLMs that might use slightly different architectures, but ChatGPT really led the way with the transformer model and with something called attention heads. And this all came about because of a paper that was written several years ago called "Attention is All You Need." And it's a really cool paper. They lay out exactly how these different layers in this engine works. So, but why is this so different, and what made it really transformative today? Like what gives it its power? Well, older approaches used something called RNNs, or recurrent neural networks, I think they're called. And they're good, but they only process text one word at a time, and they do it linearly, forward to left to right, begin to end. They don't really look at the whole sentence. They just go one word at a time. The cat is black, and that's all it kind of sees. And so they struggled with longer sentences. They couldn't really capture memory, and dependencies would kind of get lost. And the biggest limitation, and the key limitation with this, was that they couldn't easily capture long-range context. Transformer models can, and the core breakthrough came with self-attention and the attention head. So now, instead of each word only compared itself to the previous word, now each word in a sentence compares itself to everything else. The sentence, the cat is black, the is now being compared to cat is and black. Cat is now being compared to the is and black, and so on and so forth. And you'll have what are called positional encodings. So each word within the text is assigned a position. And if you have multiple attention heads, they will take different slices and rearrange these, and they'll know where they are within that context, within that input, and how that word relates to every other word within the input. So you get several views that are looking at the same sentence all at once. So one might be tracking grammar, another might be looking at subject-object relationships, another might be looking at stuff like capitalization and where does that occur within a sentence, and trying to identify, nouns versus proper nouns. Another one might be looking at the relationships between adjectives and nouns, or adverbs and verbs. So it's really cool how they're able to break this up and look at it. And then you'll have so within a transformer architecture, the core architecture is to have an encoder and a decoder. So the encoder digests the input. So we put in our text, the cat is black. And we will then assign a numerical value to different segments of that input. And there's different strategies that engineers will employ, and they all have different strengths and weaknesses. One that I've found pretty helpful for small language models is using byte pair encodings, and it's taking each character and creating a byte pair out of that, which is, I'm not going to get too into the weeds with it, but then it can also take each of those and create what's called a bigram. So then it forms a token. You'll have your single letter token, but then you'll have a token that also represents two letters together, and it's a way to create a larger vocabulary. So you have to feed the model a vocabulary, and based on your strategy, then either individual characters or byte pair characters or bigrams or subwords, words that are broken up into what are called substrings. So either words or subwords will all be part of this vocab, and each one of those will have a numerical value, and that is a token. So the model receives this input, it assigns, however it does, tokens to these numerical values. It will then go through and strip out any excess, or I shouldn't say excess, but any tokens that repeat themselves. It will then strip those out. And part of that is just to save on compute costs. It takes longer to compute more tokens, and it's a way to be a little bit more efficient. However, this led to the infamous problem where if you used to be able to do this, ask any of the models how many R's are in strawberry, and it would maybe say 2 when there's 3. And that was all dependent on how strawberry was tokenized. Now that they've introduced reasoning and thinking, a lot of these models are able to think to a degree, and they know that there are 3. But anyway, then you have to take each of those tokens, and they go through an embedding process, and they're assigned what's a vector. Now, if you remember back to, this might have been even just elementary mathematics, dealing with graphs. You have an x and a y coordinate. Vectors are multi-dimensional coordinates, and they don't just show a spot within a multi-dimensional space. The easiest way to think about this is to visualize a 3D space, okay? So you have x going across horizontally, y is your vertical up and down, and a z axis is now forward to back to add depth, okay? So think of a cube in space, okay? If you can visualize a cube in your head, this is going to be really helpful. So a coordinate would just be, within the space would just be 3 numbers, essentially. Your x, your y, and your z, that's one spot. However, a vector shows, and this is in what's called continuous space, and it shows where the coordinate originally started and where it's gone to. And this is dictated by what we call weights, and we'll get into that. Weights and biases. When you're creating these spaces, these virtual spaces, there's what's called a seed, and so based on a seeding algorithm, all of the tokens have a default start location within the space, and then as the model trains, weights are added and tokens will shift around within this space as relationships are built within them. And this is talking about this right now, getting into it. And what embedding layers do is they show all of the dimensions of this token, and they will show like how it relates to other things. And so you may have like cat, and if it's a lowercase c, part of the embedding may show that, hey, this was a lowercase c based on where it was within the sentence. So that might be embedded. That might be part of where the mapping. If it was a capitalized C, that might be in there instead. If the cat had a name then, or if cat actually was an acronym for CAT that stood for something, that would be in there. So stuff like that. And the one way that you could visualize this if you wanted to is now not only does this token within this virtual space have a coordinate that's XYZ, but now you can give it a color. So visualize a color. Now give that point a shape. It could be a triangle, and now give it a size. How big is it? How small is it? Put an outline. Like, this is all stuff that you can do within your head to kind of visualize what each of these dimensions are. And each these spaces can have like up to 1,024 dimensions, I think. Like, it is insane to try to think about. But it's really cool. So if you want to try to break your brain in a fun way, just think about that. Most embeddings, though, are maybe about 256 dimensions. I think that's about what I use when I'm doing vector stores. But anyway, so that's how the text gets encoded and put into the model. And then there will be a decoder that then goes back out and it retrieves tokens for output, and it figures out, okay, based on this input, what's the next closest set of tokens that match what would be the expected output from this thing, and it prints those out. So then they decodes those embeddings, get transformed back into tokens, and then back to that vocabulary, and then the whole text comes out. And there's usually a prediction algorithm that predicts what the most likely output will be, and the model may generate several versions of outputs, and then based on that prediction algorithm chooses the most likely. Now, ChatGPT and Llama, they're really decoder only, and they're simplified. They just predict the next word. But then you'll have different layers within this architecture of the model. So you'll have your stacked blocks of attention heads, and each one looks at a different part of the sentence. And then the text goes through a feed-forward network. And this is where these different weights are applied. So we look at, okay, the cat is black. Within the sentence, we are now going to assign a relationship to cat and is. And we see that cat is up here in, let's just for a two-dimensional grid coordinate, okay? Cat is located at 1, 2. Is located at 4, 5. Now we're going to apply some math and bring the two of them closer together. So maybe in the first pass, cat is now moved to 3 or to 2, and is dropped down to 4, 3, something like that. I don't remember what I initially said, but anyway, weights are applied to move those coordinates a little bit closer together. And then it'll do the same thing with cat and black, and the and cat. Which cat? The cat. So relationships are built, and these tokens are weights are applied to bring these tokens kind of closer together. Excuse me. And then they go through the positional encoding all over again. So each layer gets refined with this repetition. And when we do training, there will be billions of examples predicting the next word again and again and again until the patterns are deeply learned. And then the model knows the cat is black. You ask it, what color is the cat? And it'll say, the cat is black. Now, why does this matter? Well, these transformer models actually scale incredibly well. Now, why does this matter? Well, because transformers, they scale incredibly well. You can parallelize them on GPUs instead of CPUs, so graphic processing units, I think it is. And they're multi-threaded, so you can run this model, a bunch of these in parallel on the same training data to learn at a faster rate and crank through a lot more data than you could at a CPU, which is typically single-threaded. You can only do it sequentially, one task at a time, not running multiple tasks at the same time. And that's really where this raw power and knowledge came from, was OpenAI and other engineers and researchers who figured out the transformer model were able to run this in parallel across hundreds, if possibly thousands or tens of thousands of GPUs. But this is also, to be fair, this is also where some of the economic and environmental concerns are coming up, because they require a lot of power, but also a lot of water for cooling. So there are concerns there, and that's why you sometimes hear in the news about, I think in Pennsylvania or New York, or both, I think it's both actually, about old nuclear power plants that have been offline, and OpenAI is opening them up. They've paid the states and the federal government to go back in and reopen these nuclear power plants to provide power to their data centers for all of these GPUs. I don't think it's out here in Cleveland yet. There were concerns though about data centers sucking up the water from Lake Erie though, and that is also a valid concern of needing to use liquid cooling to cool these models. So these are economic concerns that we do have to be aware of. And I guess a little bit for the Catholic spin, we do have this this first vocation to care for the earth. Again, going back to the garden, man's first job was to tend to the garden. So we do have a responsibility to care for our environment. And we have to be responsible with these models, and we can't just be opening up data centers and sucking up all our resources, because we only have the one Earth. Right now, we only have a finite amount of resources. And again, people come first. We can't be taking water from people who need it. So, yeah, Transformers, ChatGPT. I hope this kind of helped shine a light into the black box of LLMs. Some people think that they're, I don't know, demons, they're spirits, they're conscious, they're awake. I mean, they're not. They're just really complicated and efficient text predictors like you have on your phone, but smarter. They can recognize patterns. They can be trained on images and music and sound to a degree. And their architecture lets them learn how to create not just words, but also create pictures and even to a degree music, because it's just numbers. That's all these models look at, so it's just numbers. I know when you work with ChatGPT on a daily basis, it can sometimes develop a personality, but here's the thing. Unless you've prompted it a specific personality, it's really just mirroring your own writing. It learns based off of how you interact with it within your account. So that's really it. So yeah, next time you're chatting with an AI, just remember, under the hood, it's just patterns stacked hundreds of layers deep. And that's all it is. Now, thank you for sitting with me and listening. I really do hope that this was informative and you learned something from it. This is my goal with the AI Catholic podcast, is to help teach people about AI and put a Catholic spin on it to a degree. Really must apologize. I'm getting over a cold. So thank you for your patience and bearing with me. Thank you for your support, for listening and watching on YouTube. Make sure to like and subscribe to get new updates to new releases, and follow us on Instagram at the AI Catholic. And on YouTube, the AI Catholic Podcast 1 is the channel that is with the number 1 at the end. So take care. God bless. Bye.